Okay, just to recapitulate in terms of kinematics, okay, we are just dealing with rigid bodies right now. One thing that we have to have in order to define the kinematics is a fixed frame of reference. Okay. In this particular set of modules, we will deal with fixed frame of reference and denote them with capital letters, capital X, capital Y, or capital I, capital J for the direction vectors, okay, capital K, capital Z for the other direction. Okay. Now, there may be many either translating or rotating frames of reference. So, let me call this as x1, y1. So, I can say I1, J1. There could be a rotating plus translating frame of reference, with respect to which something else may be defined. Just to give you an example, the earth is rotating. So, I am let us say stationed in Chennai, okay, which is just a little bit displaced from equator, and I am moving around, okay, and there is movement that I have to define, its velocity, its acceleration, but what I know is movement with respect to a particular point in Chennai. Okay. So, if I have to do that, first I should fix a frame of reference which is fixed from the angle of how Newton has defined the equations of motion, okay, and that is what we call as fixed frame of reference. I am not going to go into details of what is fixed frame of reference, let us just go with how Newtonian frame of reference has been defined. Okay. Given this, once we have an idea of how this frame is moving with respect to the fixed frame, we can bring all the motion which are defined with respect to moving frame of reference with respect to the fixed frame of reference. For example, if there is some particular body or particle, let us say P, which is defined with respect to the moving frame of reference, and with respect to this moving frame of reference, I see that there is some change that is happening to P, okay, but what I know is how it is changing with respect to this this moving frame of reference. If I have to find out what this movement P is with respect to fixed frame of reference, I have to do the transformations that we did in the last class, okay, in the last module. Basically, one thing that I have to know is, let us say this is some small o, this is capital O, let us say this is some r, let me use capital R to denote the origin of this. Then I can write what is P with respect to capital X, capital Y, given the movement of this moving frame of reference. The moving frame of reference can do two things. I am just going to stick to those which are Cartesian frames. Now, these two could probably rotate. So, this frame probably could rotate as well as move. Okay. Now, the movement of that particular frame, the translation of that particular frame can be easily defined through the change that occurs in R, and you have a rotation that takes place about a particular axis. So, I am just showing it in one plane here, it can be generalized to 3 dimensions. With respect to that axis, there is a rotation that takes place on this moving frame of reference. We use this rotation in order to define what happens to P with respect to capital X and capital Y. Okay. There could be multifarious moving frames. For example, I could be in Chennai and there is a vehicle moving, okay, inside there is this studio, let us say, and I am moving around within this studio. So, I have one frame which is Chennai, that is moving with respect to the fixed frame. Within Chennai I have a vehicle in which let us say this studio exists, which means I have another frame of reference with respect to this frame of reference. Let me call it as I2 J2, okay, and I could be moving around here, okay. Let us call this as P prime, which is Shiva moving around like this, okay. If I have to define this, I will go hierarchical way, I will go from this to this, find out what happens to this P prime with respect to P, and then to this. Alternatively, if it is possible for me to find out the movement which refers to translation and rotation of this I2 J2 with respect to capital X capital Y, then it is easy for me to write down directly what happens to this P prime, okay. So once I have a transformation available between each of now these frames, then I am done, okay. And that is basically what we did in the last class. We just stopped with just one rotating frame, but if I have another rotating frame, it is just a hierarchy of rotations and translations that I have to take care of, okay. And this is all there is to kinematics of rigid bodies. The moment we have deformable bodies, then we have to look at the relative changes within the deforming body, okay. Let us not explore that right now. Let us, having looked at kinematics of rigid bodies, we will look at kinetics. What is kinetics? Kinetics is the one that relates kinematics or the motion to the forces, okay, and it relates these two through a law. In this particular case, we use Newton's laws in order to relate them, okay. In most of the laws, you will have a kinematic quantity and a kinetic quantity, and the relationship is proposed by the law, okay. Some people call it as Newtonian principles or Newtonian laws. The difference is a debate that still goes on, okay. So, I am not going to go into that. So, given this, let us say I know kinematics of the body, let us say I know the kinematics of the rigid body. And I now wish to relate the forces acting on the rigid body to the kinematics, okay, and that is what I want to do. So, let us look at how we can do that. Let us say there is a rigid body, okay, a fixed frame of reference that I always use. Let us assume for now, with respect to fixed frame of reference, I know all the quantities, especially the acceleration quantities, okay. The first exercise that I may do is to look up the acceleration quantities with respect to fixed frame of reference. Given that, I can now proceed to look at the equilibrium of this. Now, when I say equilibrium here, I am talking about satisfying Newton's laws, okay. And what does Newton's law state? F is equal to ma, right. There are two things that happen here. This is okay for a particle because there is no resultant moment that we are looking at. In a rigid body, however, we have a moment as well as a force that appears, okay. The force is directly handled through F equals ma, and the moment has to be handled appropriately, okay. I am going to look at the result first, and then we will go back and find out what the quantities are that we have in the law, alright. So, let us say I have a rigid body here and whose mass is already known, which is m, okay. I wish to find out the relationship between acceleration and force. Okay. Let us say for now there are some external forces acting on the body. So, let us say F1, F2, let us say there is a moment M1, let us say F2, F3 and so on. In statics we already looked at this particular type of set of forces and found out how to write down the static equilibrium equations, right. What we did there is we looked at all these forces, finally we put them all together and said there is a resultant force and a resultant moment at a particular point that I can take, okay, where this is sum of all the forces and this is sum of all the moments and the moment of the forces. So, M is sum of all the moments plus sum of all the Ri cross Fi, alright. This is basically what it is. We did this exercise in the statics problems. Given a particular point we did this, found out these two and said since there is no acceleration this should be equal to 0 and this should be equal to 0, so that we have equations that solve for a static equilibrium requirement of the rigid body, okay. Now it is a natural extension that I want to bring in, which is it is no more in static equilibrium, it is in motion, okay. The motion could be constant velocity, which means acceleration is 0, or you could have constant angular acceleration, etc., etc., okay. Now as far as the force resultant is concerned, I can look at this particular rigid body and focus on this particular point. Let us say I am going to call this point as P, okay. I have looked at the resultant moment and resultant force at this particular point P, okay. Now what could be happening to this rigid body? This rigid body could be moving so that P moves along, and it could be rotating with respect to P, pivoted about P, okay. As we have already talked about, we can take any point on the rigid body and describe the motion of the rigid body through a single translation of that particular point in question and a rotation about it, okay. Supposing this rigid body has taken another shape over here, we did this exercise earlier, and if this is the point that we have as focus, the first thing that we could have done is do a rigid body translation like this, so that you get something like this, and a rotation to accomplish the configuration that we have here, okay. Given this, I can describe the motion of this rigid body with respect to this reference point P as a pure translation and a pure rotation, okay. And therefore I can attribute the translation to F and the rotation to M, simple, okay. So what should I write? If the translational acceleration of this rigid body at point P is, let us say, AP, okay, and the angular acceleration, so I am just going to say this is AP, it is a vector, and let us say there is an angular acceleration, okay. Is this a vector? Yes, this is a vector, because you will have an axis about which it is rotating, alright, and there will be an angular acceleration. Knowing these two, it is possible for me to now I am ready to write down the Newton's equations, okay. Looks simple, but there are many other derivations that are involved in order to arrive at this particular thing, alright. So let us just move on and write down. This is no more valid. What I will do is I will chop off this and chop this off. Since it is an acceleration, and it has to obey Newton's laws, it is equal to total mass times AP, because the force resultant in question that I have found out is with respect to P, and I find the acceleration of that particular point in the rigid body, that is AP, and I get an equation. Remember this equation, F equals MAP is a vectorial equation. How many components? F has 3 components, A has 3 components, which means 3 equations I can write, x, y and z, alright, in a Cartesian system. I am just going to stick to Cartesian system, so it is easy to talk about all these things. Okay. The other is moment. What result do I get? Again a very simple result we get. M happens to be the same thing I can take, alright, but the right hand side now will be some I times alpha. And what is this I? I is the polar moment of inertia about P along the axis of alpha. I will repeat this again. Supposing it is having an angular acceleration about an axis, and I know the axis, I will take that axis passing through this P and find out the polar moment of inertia IP, and that will give me M is a vector, alpha is a vector. If you look at this, I will get an understanding of how it is occurring. Okay. Remember in this equation these two are coaxial in the sense that the direction of AP relates to the direction of force. Similarly here, alright. Now how many equations do I get? I get one equation here, another equation here, a vector equation and a vector equation, which means 3 plus 3, 6 equations. So I have 6 equations just like in static equilibrium. Okay. There may be unknowns here, unlike here which is right hand side equal to 0 in the static condition. Here the right hand side quantities also may be unknowns. Okay. So we essentially the problems related to kinetics will involve basically unknowns to the right hand side or a left hand side, and most of some of the literature talks about this as a inertial force. I would avoid that, I would go for F equals ma directly, because this completely defines the law that I am using. Is this clear? Knowing this, I can do kinetics directly. What are these AP and alpha? They are accelerations and angular accelerations and linear accelerations with respect to a fixed frame of reference, that is described by F equals ma. That is very important to know. Okay. You would have done this exercise earlier, but I am just stressing this over and over because many times we make a mistake in this particular from this particular angle. Okay. Fixed frame of reference, that should get fixed in your mind. Thank you.